Welcome you all to this educational video in which we will see how the Rydberg's mathematical expression helps in predicting the wave numbers of lines which are observed in the line spectrum of hydrogen. In the previous video, we had seen how Balmer could predict the wave number of visible lines in the line spectrum of hydrogen. He expressed an equation which is given like this: wave number equals 109677 multiplied by 1 by 2 squared minus 1 divided by n squared. The value of n, it can be 3, 4, 5 or any numbers which is more than 2, not 2 or below that. It should be always more than 2. So accordingly, he substituted in this particular equation. He got 109677 into 1 by 2 squared minus 1 by, first he had put the value of n is equal to 3 squared, then he had put the value of 4, 5, 6, etc. And he observed that all the visible lines which were observed in the line spectrum of hydrogen, they matched with the wave numbers corresponding to the value of n equals 3. That case, the wave number he predicted was 1523, which was close to the wave number of red light which was observed in the line spectrum of hydrogen. Then he had substituted the value of n is equal to 4, 5 and 6, and he observed that the wave number in each case, that is for the value of 4, 5 or 6, in each case it correlated with the wave numbers of the corresponding visible lines, that is green light, blue light as well as violet light, which was observed in the visible region of the line spectrum of hydrogen. But the limitation of this Balmer series was that he could predict the wave number only for those electronic transitions where the electrons fall from a higher orbit to the second orbit, and that too only to the visible region of the line spectrum of hydrogen. In fact, we should understand that apart from Balmer series, there are other series also present in the line spectrum of hydrogen. They are we have the Lyman series, which results from the electronic transitions from a higher orbit, say the second orbit to the first orbit, or third orbit to the first orbit, or fourth orbit to the first orbit, or in short, whatever lines the hydrogen will emit when the electrons jumps from higher orbit to the first orbit. You call them as the Lyman series. You call them as the Lyman series. So whatever lines the hydrogen will emit when the electrons jump from higher orbits to the first orbit, you call them as the lines which belongs to Lyman series. But the limitation of Balmer series is that using the Balmer equation, you cannot predict the wave numbers corresponding to the lines which are emitted or the radiations which are emitted when electrons fall from 2 to 1 or 3 to 1 or 4 to 1 or any higher orbits. So there lies the importance of the Rydberg formula. So this particular formula was developed by Johannes Rydberg. That is his complete name. So he developed an expression. It's given like this: wave number equals 109677 into 1 by n1 squared minus 1 by n2 square. Here n1 represents the orbit to which, the lowest orbit to which the electron is falling, and n2 represents the higher orbit from where the electron is falling. So let us apply this to the Lyman series. So in the Lyman series, the first electronic transition that can happen is when the electron can fall from the second orbit to first orbit. So in that case, the nu bar will be equal to 109677 into 1 divided by, so to the orbit to which the electron is falling is first orbit, so it will be 1 by 1 squared minus 1 divided by the orbit from where it is falling. It is from the second orbit, so that will be equal to 1 by 2 squared. So if we can work it out, the final value we will be getting it as 82,257 centimeter inverse. So it is 82257 centimeter inverse. This belongs to the ultraviolet region of the electromagnetic spectra. Practically, if you observe the first line of the Lyman series, that means that which arises from the transition of electrons from the second orbit to the first orbit, you can see that this practical frequency or the practical wave number of the first line, it very well correlates with this theoretical value that was predicted by Johannes Rydberg using the Rydberg equation. So in the Lyman series, you are able to account for the wave number using this particular equation. It doesn't stay only with the first number. It is true for all other numbers also, all other lines also. Like for example, if we consider the electron to be falling from the third orbit to the first orbit, here the value of n1 will invariably be 1 because that is the lowest orbit. The value of n2 will be equal to 3 because already 2 we have considered. That is the first line. Second line, if we can substitute here, that is 1 by 1 squared minus 1 divided by 3 squared because we are considering the second line, 1 by 3 squared. So the equation comes out to be equal to 109677 into 1 by 1 squared minus here 1 by n2 will be equal to 3. So it is 3 squared. So 109677 into 1 divided by 1 minus 1 divided by 9 centimeter inverse. So this, if you work it out, it comes to 97,490 centimeter inverse. Again, the second line of the Lyman series, which symbolizes or which corresponds to the transition of electrons from the third orbit to the first orbit. If you can find it practically, it will be close to 97,490 centimeter inverse, which is the wave number that is predicted by the Rydberg formula. So likewise, you can account for the wave number. You can calculate the wave number corresponding to the transition of the electron from any higher orbit to the first orbit. So all the lines in the Lyman series can be accounted with the help of this formula. That is the formula which had been put forth by Rydberg. And it doesn't end only with Lyman series. It's applicable for all the series like Paschen series. Then we have the Brackett series, the Pfund series. For all series of lines which are observed in the line spectrum of hydrogen, this particular equation holds true or it is valid. So in case of Paschen series, if you apply the formula 109677 into 1 by n1 squared minus 1 by n2 squared, as we know, in case of the Paschen series, it arises from the transition of electrons from higher orbits to the third energy level. So in that case, always the value of n for all the lines in the Paschen series the value of N1 will be equal to 3 and the value of N2 will be more than 3. So it can be the from electronic transition from 4 to 3, that is the first line, 5 to 3, it will be the second line. So in all these cases, if you can check the wave number, making use of this Rydberg formula, it will correlate with the practical value of the wave number of every line that you see in the Paschen series. So here lies the significance of the Rydberg formula. So that is, in case of the Balmer series, when you are able to predict only the transition of the electrons when it falls from higher orbit to 2 using the Rydberg mathematical expression, you can predict the wave number of every lines in the line spectrum of hydrogen. That is, electronic transition happens from any higher orbit to any lower orbit, including the Balmer series. You can predict it with the help of the mathematical expression put forth by Rydberg. So that is the importance of mathematical expression put forth by Johannes Rydberg. If you felt this video to be helpful in understanding the concepts of chemistry, please do share it with your friends too. Thank you for watching this video. Have a nice day. Goodbye.